Today we will study about a very fundamental data structure called Trie. It's also called Prefix tree. And why it's called Prefix tree, we will see in a minute. First, why this name Trie? So from what I know, it comes from the word retrieval. So if you add VL in the end and RE in the beginning, this makes the word retrieval. And in general, it comes from information retrieval, or in particular text retrieval. So this means retrieving the text. You have a defined set of text and you want to extract some information out of that. You want to search for some text. So there Trie is useful. And in order to motivate why we need a Trie data structure or a prefix tree, let's see. First, let's understand this Trie data structure. So in order to search for any word, you need to have some words on which you want to perform the search. Let's say you have a book and you want to search for any prefix on the words of that book. So what you will do, first you will need to store those words. Only then you can search on them. So let's say I want to insert a word apple. So what we will do, for each character, we will have a node here. So we have a Trie node. And we will have a Boolean, is end or is leaf. So for example here, for A is not the end of any word in the text. Let's say we have another word, apples. So you see that A is not end of any word. If we add A, then it will be end of a word itself. This is a word in itself. But let's say this is not here and this is not here at the moment. So we create a node. There is a root node which does not store anything. It will have 26 children. If we are just working on English small letters from A to Z, there are at max 26 characters and no other characters. Then we can have one node for each. First children for A, second children for B, and all the way up to small g. You must know the tree data structure, a binary tree. We know that it has a left child and a right child, and these are themselves pointers to nodes. With the same analogy, you can relate this, that instead of having just left and right, it will have 26 children. Children number 1, 2, 3, 4 till 26. So initially it's empty. We have not stored any word. So first we store A. So what is the position of A? A is at position 0, G at position 25. B will be at position 1 and so on in sequence. So we see that A is the first child. So we go to the first child node. We see if it's pointing to a Trie node or not. Initially everything will be pointing to null. So we see that it's pointing to null. So we will create a new node. And again it will have 26 pointers all initialized to null. And next we will come here. We will see next letter is P. So we will take P is 16th character. So we will take the 16th child and come here. We will see if a node exists or not. If not, we will create it. And we come here. Again, next is P. So we again look at its 16th child. Again, if it's null, we create one. And it will have 26 null children. Next we come here, L. So L is 12th character. So it should look at the 12th child. Again, it's null. So create one node. Next it will come to E. So it will pick the 5th child pointer. Create one since it was null. And then it has reached the end of this word. So what it will do on the last word that we inserted, we make its is leaf or is end of word true. For others, it will be false. So that next time, let's say I want to search APP. So we will see that if first child is null or not. If it's null, we will return false. I did not find it. Here we are doing search, and here we were doing insert. But if it sees that A is there, so this is fine. We will go to next character, P. So we will look whether this P child is present or not. It's present. Next, again P is present. So we come here, and we see that we have reached the end of search term that we want to search. So we will check if the end of word is true for this or not. So we see that its end of word is false because we had set true here. So we will return false. I did not find app. So you may be thinking that app is contained in this apple itself. So why we need to return false? So for that we have to implement another function. It starts with. So search will do exact match if this word exists in the corpus, and corpus is a generic term that's even used in NLP terminology for a exhaustive set of words on which you will be performing some task. So if a word starts with app, this should return true. But is the app exactly present in this trie or not, or the corpus or not? We will return false. And we also need to implement insert logic. So we have to implement these three functions in this question. And I am talking about a simpler version of this. You may be thinking that there is an unnecessary wastage of a space. We are storing 26 nodes at each of these, and only few of them may be used actually. So let's say there is a word apple, there may be a word bat. So it will come here, B will be initialized, then its first child, and then its 20th child, bat. But you see, lots of them are not used. So why we are storing it? So this assumption simplifies the implementation, that here we are working with just 26 characters, and it's given in the question. If we are working with a large character set, for example, directly we can add capital letters as well. So it will make 52. Then we are working with numbers. So we add another 10 character and some other characters as well, like apostrophe S or this single quotes, double quotes. If these are searchable, then this character size will become very large. And there we will use an optimized version of this, where we will create a trie node. And instead of having a fixed size array, we will have a hash, empty hash initially, and whenever we encounter any new character which is not in the hash, we insert it into the hash. So for example, in this case, there are words just starting with A and B, if we have inserted these two, or if I have inserted apples also, 3 words, but still 2 of them starts with A, 1 of them starts with B. So for this node, only 2 of its branches are used, rest are not used. So first time, so its map will contain A and B, and this internally will have their own maps. So instead of fixed size arrays, we can replace it with maps so that it saves a space. So we will see it in a separate video, this implementation of this. This is a much simpler implementation, and we will exploit this thing that is given in the question, that we have just 26 characters. Now, why do we need this prefix tree? Why cannot we just store them in some array simply, like apple, app, apple, and bat? And when we are asked to find whether apples exist or not, so we will start searching here linearly. We will look here, matches, matches, matches. We reach the end. We did not find it. So we go to the next word. Again, start the search from beginning, A, P, P, L, E, but S is not there. So we move to the next. So we see that we are doing repeated search. APP we have already searched. Still we are doing APP here again. If this prefix exists in 1,000 words, we will repeat this logic 1,000 times. But here, will we ever repeat the logic? No, because all the words which start with A will lie in this branch only. So once we search for A, we will never search for A again. Next, all the words starting with AP will lie in this branch only. So let me use a different color. So all the words starting with A will lie in this branch and none of these. So we will never search for A again. And all the words starting with AP will lie along this branch. And we will only look for other characters. We will never have to search again for AP. So we have already here. We will come here. So we are saving all of those repeated computations if we are using a trie. And here, what will be the order of search? We just do one pass of this word. Let's say I'm searching for APP. So I will take the branch corresponding to A. Then we will look at next word, next character, which is P. So I will next take the branch corresponding to P. So I come here. Next is again P. So we again take the branch corresponding to P and we come here. And either we will return true here or false. One of these. We will not need to do any other searches depending on whether this is end of the word or not. So it will take order m time. If m is the length of the search word, the search will be taking order m time. Similarly, inserting is very similar to search. In order to insert, first we search whether it's already present or not. If it's already present, we don't insert it. We move to the next and keep doing that until we find a null or we find the word itself in the trie. So insert will also be order of m. And starts with is same as insert with just one difference that here we will not check end of word. So it's again order of m. So all of these are order of m. That is the search term or the word that we are working on, inserting or searching. And space can be, for each node we have 26 children. So 26 times, let's say there are n words and each word length is m. You can take some average number, sets of this order. So let's see the implementation of this in C++ and Java and Python. So first let's add some member variables here. We will have a pointer. Just like in tree, we add tree star left, tree star right. We will here add 26 of those. Children 26. And I am using 26 only because they have mentioned it. It's just from A to Z, small letters. Next, a bool flag is end of word. These are the two variables we will need. Then we will initialize. So let's by default keep it false, and for int I equal to 0, I less than 26, plus I, children I equal to null ptr. So everything is null. All the children are nulls. Then we will insert a word. So for that, the current pointer will be this node, the root node. And so wherever we start this insert, so how we will use it? We will use it like this. We will create a new trie. So this is pointer to a new trie node. So this is a class trie. So inside this, this pointer will be pointing to the instance of trie, this instance of trie. So let's say I create two tries, trie1 equal to new trie, trie2 equal to new trie, two tries. So when we are inserting in trie1, so when we write trie1 dot insert, this pointer will be pointing to trie1. When we do trie2 dot insert, this pointer inside this class will point to trie2 pointer. So this pointer is a pointer which will point to a particular instance of that class and not a generic class. So here this denotes that trie instance on which we are inserting it. And then for char c in word, if not current, c, and we need to subtract the ASCII value of a. So for a it will be 0, this index. For capital G it will be 25. So if this node is empty, then we will create it. And by default it will initialize it to false, is end of word. And then we will advance it, current equal to so we insert it and move the current there so that we can insert the next word, next characters. And when we have inserted everything, all the characters of this word, the current will be pointing to the last trie node corresponding to the last character of this word. So whether that was created or that was already existing, current will point to that trie node. So we will set current, then is end of word equal to true. So we have done the insert part. Next, search. So again, the logic should be very similar. So current is this node, and then for each character, we see if it's not there, that is it's null, then we return false. But if we did not encounter any situation like that, that is all the characters of this word were present, so at the end of this loop, we will reach the last trie node. But that may not be the end of word, so we will check if it's end of word, then return true, else we will return false. So search is done. Next will be starts with, and it should be almost similar to this search. So just this word is changed to prefix, and this check is not required. Just this check is required, and here we should return true. So let's try. So this works for this case. Null, null, no, there is some wrong answer. So we will see why. False. Search is returning false for app. So there is some error in insert. It's not able to search app, although we have inserted it. Let's see where else it's wrong. Null, null, next is false. Third one is false, that is search. Again search. So search is always returning false for us. So here current is never updated. It's always pointing to that trie node instance, the beginning. So it will never search it if it's not one character. So we will first make current equal to this thing, and if not current, then return false. So this way current will always get updated to the next try node if it keeps finding that. So hopefully this should fix. We need to change here also. So let's try again. Now null, null, true, false, true, null, true. Now it looks like it's working. So let's submit. And the solution is accepted in C++. Now we will just repeat the logic in Java. So let's copy a few things. We will need to do it in steps here, since they have added template for different functions. So it's private try children, and it will be Boolean. Then we will copy the insert code. So let's see if it works in Java or not. Cannot find it. Okay. So it's prefix here. This. So it's giving the correct result for this case. So let's go ahead and submit. And it's accepted in Java as well. So there is no change in logic here. If you understand C++ code, you will understand the Java and Python code as well. So here, again, we need to copy it. Is end of word and children. False, and children equal to an array of 26 none values. Next, we will copy the logic of insert. to get the ASCII value of a character, you need to use ORD here in Python. Is there some mistake here? So next search. So let's see if it works or not. So this works for this case. So let's go ahead and submit. And the solution is accepted in Python as well.